Hello, welcome to session number 27 in the series Microwave and Millimeter Wave Circuit Design. My name is Anurag Nigam, and the current topic we are dealing with is power amplifiers, right? So we have broadly categorized. So in this session, I'm going to focus on Class E amplifiers. So my main focus is going to be on Class E amplifiers. Okay, there will be some adjacent topics which I will just mention. Okay, so power amplifier, just one second. A power amplifier can be categorized into two categories mainly, or rather three categories, right? One is called non-switching amplifier. These are mostly linear amplifiers, right? And then there are switching amplifiers. And then there are mixed mode amplifiers. Okay, so a non-switching amplifier, for example, is most common is A, B, B, and C. Now, in non-switching amplifier, the device acts as a voltage controlled or a current controlled current source. So device is voltage or current controlled current source. Okay, that is that you are operating an amplifier in the active region of the device, right? Now, a brief note on what is a Class A amplifier. If you are biased at the center of the load line, right? So if I take a device, somewhere I have chosen a bias point, right? So these are the characteristics of the output characteristics of the device. A typical, it can be a FAT, it can be anything. Just one second. Right, and I have chosen a certain load line and I have basically biased it. So this is your current and this is your voltage. So I am going to swing around this. Okay, so this Class A amplifier is going to be up to a point where I'm swinging the entire region, right? So this is we are going to plot in simulation also. When you do a Class A amplifier, you will see that this is how we swing, right? Now this can be a drain current and the drain voltage, or it can be a collector current or a collector voltage. HBT or FET, it's going to look the same. Now what happens is, if we are going to, so now in this case, a maximum efficiency of 25% is possible in a Class A amplifier. So let me change the color. Okay, so we are talking about 25% efficiency. Now, if you couple the output using a transformer, for example, you can get an ideal 50% efficiency. So this is what a Class A amplifier is. And if you look at uh, how much maximum power you can deliver, right, for a given stress level, right? So how much power can you deliver for a given stress level? So let's say P max divided by uh, P max divided by P stress. So basically you choose a device of a certain size and it has a limitation on the currents and it has a limitation on the voltage swing across it. So that maximum current of a device to a maximum voltage of a device multiplied to a maximum voltage of a device, that is going to give you a P stress. So P max, which you can deliver by P stress, is known as device utilization factor. And for a Class A amplifier, this is going to be 12 this is going to be 12.5%. So that means that if a device is stressed at a certain, let's say 1 watt, okay, so then you can deliver only 12.5% of that 1 watt, right? So this is an example of a non-switching amplifier. Now if you keep, okay, if you lower the biasing, okay, so basically you reduce the drain current for a given this thing, so you are choosing a higher impedance load line. Okay, so if you keep reducing the current, the DC resistance shown to the device is going to keep increasing, right? so if you choose a high impedance load line, right, or you lower the quiescent current, so what you expect in terms of swing is going to be like this. Let me just draw this. So if you go to class AB, okay, and this is IT, this is VDD, okay, so I am somewhere, let's say I have chosen somewhere lower point is around here, okay. So now I swing, okay, so to some extent it is going to be looking like class A, but soon you are going to start clipping this waveform. So when you start clipping the waveform, okay, the DC value of the DC value across power goes up. So if I was to draw that class AB, what is going to happen is, and I am going to plot P out. So I'm starting with ICQ, quiescent current, and I have biased it low, and it is going to pick up like this. Okay, so the clipping causes the DC level to shift, and that causes that changes the DC bias. Okay, and we say it is RF biased once this happens, right? So this happens, what is going to happen? The efficiency is going to go up, right? The efficiency is going to go up, but the device is going to start, you know, compressing. It is going to compress when the current is reaching the limit. So initially what happens is, if you keep on increasing the power, the current drawn from the drain increases above ICQ, right? So if it keeps increasing and there is no restriction, you can deliver more and more power at a higher and higher efficiency. The clipping is going to increase, right? The clipping is going to increase, and you are going to have more DC current, right? But then there is a limitation on supply for this current, or there is a limitation posed by the channel width for a device, right? And that when that happens, the device compresses, right? So if you were to plot the gain versus P out, what's going to happen is, for a class AB, because the gain is going to increase with the bias, so it's going to increase and then it is going to compress, right? So let me just do one thing. Let me match the curves. So when it is ICQ and then the current builds up, and then there's a gain expansion, right? It may not be as pronounced as I have drawn, but I'm trying to say is that as you increase the power, okay, the gain is going to expand before it compresses. So this is a typical of class AB, and the efficiency numbers are going to be between 50%, and it's going to be between the limiting case of pi by 4 into 100%. That is going to be like 78%. So this is what a class AB would do, right? Now if it is a class B, so I have biased at the cutoff, so current is going to be 0. So you are going to allow only what you call 180 degree of conduction or less, 180 degree of conduction. So when you allow 180 degree of conduction, okay, the efficiency is going to be more. It's going to be 78%. So in a class B, so let's just label this. So we are talking about class A here. Okay, now we are talking about class B or AB over here, and then we are talking about class B here. So if you were to compare in terms of conduction angle, okay, so here there is a 360 degree of conduction angle, Okay, over here you can see there's going to be between 180 degrees and 360 degrees of conduction angle. This is AB. Now when you talk about class B, you have exactly 180 degree of conduction. Efficiency ideally is going to be 78%. You can derive this from the active region. Okay, so you are going to have pi by 4. Okay, times of, because this is almost half wave rectified, right? So if it is a half wave rectified, the RMS value is going to be half, right? And the when you multiply the two, there is a factor of 4. So that's the efficiency you're gonna get. Okay, so this is a class B amplifier. Now if you want to have a use class B or AB for linear application, you can put them in a push-pull configuration. So basically you can take and conduct 180 degrees from one device and then another 180 degrees which is negative in the from the other device, and the load is basically is not grounded. It's basically a floating load between the two. Or you can also create a grounded load depending on the output matching. Now there is going to be a crossover distortion. Okay, so to avoid crossover distortion, instead of having a class B in push-pull configuration, you can slightly bias it up, right? So that when it turns on, when the power is whenever there is a wave which crosses 180, you have already got the other device which is already pre-biased. So this will remove the crossover distortion, right? So then in that case the efficiency possible is going to be 78%. Now if you look at a conduction angle which is less than 180 degrees, so that would be class C. So basically if you bias it well within the cutoff, or you bias it negatively, then what's going to happen is you are conducting less than 180 degrees. So class C is going to be conduction less than 180 degrees. When this happens, let's say 120 degrees is the conduction angle. At that point the efficiency is roughly 86%, right? Now if you have a conduction angle of 0, then the efficiency is 100%, but then there is no waveform actually. So that's a hypothetical case, that here efficiency is at 100%, but then you are not swinging in the active region, so you are not delivering power. So in that case, class C amplifier at, let's say, typical 180 degrees, efficiency is around 86%. Conduction angle is 120 degrees. Now in this case, let's look at the device utilization factor. For class AB, the device utilization factor is going to be, or even B, is going to be 12.5%. This is going to be the device utilization factor for class A or class B. Now when it comes to class C, okay, at 120 degrees, the device utilization factor, this is at 120 degrees, is going to be 0.0, or rather 9.81%. This is a typical number where other amplifier topology, okay, which I'll come to later on. Now in class C this is happening. Now so for linear applications, you are going to use something like a class A or a class AB, right? You can use a class B in a push-pull configuration, right? Or rather two-pole configuration, right? So this would be a push-pull class B. Now in all this case, the device is acting as a voltage control current source. Now notice why the efficiencies and numbers are small. This is because the device dissipation is dominant over here. Why? Because when there is a current in the device through the channel, there is a voltage across the channel. So voltage and current exist simultaneously, right? So there is going to be a dissipation. So let's say if I was to do a limiting case, okay, so let's say these power amplifier guys will know it. If I look at, I have compressed the AB or a class B or a class APA, then the swing is almost like this. So basically the swing which you are going to see is going to be almost like this. Hang on a second, I'm not good at drawing. Okay, so this is going to be the swing, and the device characteristics are like this. Okay, so notice that here when you are traversing over or traversing over here, you are seeing the maximum dissipation. But when you are traversing over here or here, you are not seeing dissipation, right? So this gives you another idea. Okay, now let me plot this. Let me just label this. This is going to be ID. This is going to be, okay. This is what happens when you compress a PA. It's going to make a full swing of the active region, but then most of the dissipation is coming from this portion of the swing, right? And if you draw this in time domain, okay, so you are going to have voltage waveform something like this, then you're going to have current waveforms like this. So basically you have flattened the waveforms, right? So most of the dissipation is coming in this region or this region where we are traversing these portions. Okay, so most of the overlap basically is the cause of the dissipation, right? So in this case I am plotting voltage, drain voltage or a drain current, and this is time. So this is what happens in case of A, B or A or B when it is compressed. We can plot this and see what is happening. Now, why the amplifier design is so important, in the sense so critical? This is because unlike passives, in passive the impedances are fixed, but in case of actives the impedances are not fixed because the bias condition is changing. Okay, so ICQ is the small signal. So if you match it to ICQ, you have matched the amplifier at a small signal. But once you hit it with power and starts compressing, the drain current goes up, and then as the device as parameters are going to change on input and output, so that's going to cause the change. Okay, so the idea is if you are best matched at the compression, as we have covered in the previous session, right? On PA, you can refer to previous section where I have discussed this, right? Now let's say another breed of amplifiers which is called switching amplifiers. So I will put here E, and I am not so well informed about F and D, but I have some information about it, so I'm going to just share it. Okay, so let's come to Class E amplifier. Now in all this case the device acts as a switch. So a switch ideally, okay, a switch is like this, right? This is under the control of a control signal. Okay, a switch ideally would have a zero resistance when it is on and infinite resistance when it's off, right? So now when this is done, then when the switch is off, then because of the infinite resistance there is no current, right? So when there is a voltage across the switch, there is no current when it is off. When it is on, there is a current. So let's say when it is on, there is a current through, but then because of the internal resistance being zero, then the net voltage across this switch is zero, right? So voltage and current are in quadrature. Now under compression also, you will see that the voltage and current are in quadrature, right? In any amplifier under compression it's going to happen. Voltage and currents are in quadrature, right? That's why the efficiency number goes up with the power. So if I was to plot efficiency, like for example here I have plotted gain, if I was to plot efficiency, the efficiency is going to start this way and it's going to build up, and then it's going to compress. This is because the device dissipation is going down, okay, because we are having less and less overlapping region between voltage and currents. Okay, so the device dissipation is going down. That's why the efficiency is shooting up with power, right? Now here what's happening is I have voltage and current in quadrature. Now if I was to connect the switch across the load, I'm going to have a power delivered of 0. Power delivered. So in a switch the power delivered is going to be equal to 0 because the device excuse me, the device basically uh, is not able to put a active power. Active power means that the voltage and current are in phase. Now if I want to use this in some form of an amplifier, I have to do this impedance transformation. So over here there is a switch, and then there is a load network, and then there is a load. So the function of this load network is to transform the phase and voltage, phase and current relationships are in quadrature here. Voltage and current are in quadrature. Okay, so that's why the switch dissipation is 0. But then it's a function of load network to cause this quadrature to vanish, or rather the V and I are going to be in phase across the load because it's a resistive load, right? So it's the function of the load network to do this, right? So this is how a switch can be used as an amplifier, and the load network basically is doing the in phase relationship coming out. Okay, so it's still a switch, and switch has a 0 dissipation, right? So the efficiency is going to be 100%. And which efficiency am I going to I'm talking about? It's going to be your drain efficiency. Okay, P out divided by PDC. So whatever power, and I'm assuming that the gain is high, that's why I can say that. Okay, so an ideal switch doesn't require a lot of power to switch it. That's what I'm assuming. So the gain is going to be very high. Okay, so now in this case, right, this is what a class E would do it. Class F would do it the same way, but there are different categories of class F. So a class F basically is divided into F, F2 and F3. Now again, the switch has got voltage and current relationship in quadrature, but then the load network causes them to be right in phase across. They have to be, right, with the minimum loss across this load resistance RL. Now there is something called maximally flat class F. Okay, so a maximally flat class F is going to cause the voltage and current waveforms to flatten quickly. So basically, instead of flattening over a range of P out, instead of taking this range of P out to flatten, if I can cause the flattening to be early. So how do I cause the flattening to be early? So if you look at the voltage and current waveforms across time, okay, you see this more like a square wave. And what does a square wave, Fourier expansion of a square wave show you? It is going to have fundamental, it is going to have third harmonic, okay, so third harmonic, fifth harmonic, seventh harmonic. Okay, so if I was to compress this, rather, if knowing intentionally, if I want to compress a device faster, okay, so what I'll do is I'll put something called idlers. Okay, so I will put here something called idlers, which are going to open. So an idler would be typically, let's say, this circuit. Okay, so at, let's say, at thrice of f0, I have an idler. So that means that this is going to anti-resonate at third harmonic, and then I have an idler at fifth harmonic and seventh harmonic. So this will cause all the odd harmonics to be able to propagate to the device, and then to the load, and then you are going to have this square waveform of voltage and current. Okay, so you have a square waveform of voltage and current. Okay, at the same time, what you have to do is you have to short out the even harmonics. So basically, if you short out the even harmonics and open out the odd harmonics, then you maintain a quadrature over here, and then the load network is going to, okay, be delivering all the odd harmonics and fundamental to the load. So what's going to happen? Okay, what's going to happen across the device is voltage and currents are in quadrature, but the smaller device, okay, is compressing faster, right? So a smaller device, but it is delivering more power because you have flattened it. So for a given stress level, so stress, basically P stress depends on the size of the device. So for a given stress level, you are delivering more power by doing this kind of network. So this is called maximally flat class F amplifier, and this is F1. Okay, so in this case, this was patented in 95, I guess. Okay, so here the efficiencies are ideally 100% again, because the device dissipation is 0, and then the load network is ideal or a high Q, right? So in this case, what happens is, for a given small size device, you are able to deliver more power. So that means that the device utilization factor for class F1 is going to be 15.9%. So you see that I can deliver power from more power from a smaller device. Okay, and then the efficiencies are going to be, ideal efficiencies are, drain efficiencies are 100%, right? So this is going to be class F amplifier. Now if I take two class F amplifiers and use this in push-pull configuration, right? Okay, so I have some form of a two-pole switching amplifier. That would be class D amplifier. So in this class D amplifier, okay, the device utilization factor twice of 15.9. Okay, okay, so the device utilization factor would be 9 to say 18, 1, 31%. Okay, so class D amplifier is going to be more linear than class F, but then it's able to deliver more power for a given device sizes or device stresses, right? So that's why this D amplifier is very good for delivering power. Now there is class D amplifier is basically a band limited amplifier, or rather it's a band pass filtering at the output. Class S amplifier is also there. That's a similar concept, but with a low pass filtering at the output. Okay, so class S amplifier is similar to class F amplifier in that sense. Now I have left out the last category, which is a class E, because I'm going to model this class E in this session using Matlab, using equations, and then basically I will do trade-offs, right? So there are closed form equations which I'm going to derive for class E, and so that you can study, okay, what are the effects of, you know, various inputs or various specifications of a class E. Okay, so let's now dig into class E amplifier. Okay, so let me just first draw a class E topology. Class E topology. Okay. Okay, a class E amplifier consists of a switch and a supply. So let's say this supply is VDD, and then there is what is called an RFC. This is an ideal choke. It has zero resistance at DC, but infinite resistance at any frequency, at any frequency, right? So what does it mean? It means that I have converted a voltage source into a current source, and the current drawn is going to be ID, and at any other harmonic or any other frequency the currents would be not there, so only the DC current is there, and that's why the voltage across RFC is only going to be DC voltage, right? So a voltage ideal voltage source is converted into a current source if I put a radio frequency choke. Okay, after that I am going to put this current through a switch. So basically a class E topology is going to chop the current. Okay, so it's a current chopper, and then I am going to have a shunt capacitor, right? So let me see if I'm recording. Okay, so I have a shunt capacitor, then I have an inductor and a capacitor and a load. So this is CS, this is LS. So this is voltage mode class E. So if you can have a dual of this, a current mode Class E. So let's first discuss how a Class E operates and why the efficiency is 100%, right? So a switch basically is chopping the current, right? So let me just draw this. Okay, so we know that the voltage across the resistance or the load and the current are going to be in phase, and so if the voltage is C, the current is going to be C by R, right? So I can write this. I can write VO is C times of, let's say, sine of omega naught t plus, let's say, arbitrary phase phi. Then current is going to be equal to C by R times of sine of omega naught t plus phi. Now this is operating at f naught. Okay, now if you, before I go into mathematics, I will explain how it works, right? Okay, so now let's see what's happening in terms of circuit before we go any further. Okay, so I'm operating this switch. Okay, so I'm operating this switch at f naught or omega naught, right? So when the switch is off, okay, so there is a circuit over here which has got CS in series with CSH. So C equivalent in this case is going to be CS. So it's going to be a parallel combination, right? So 1 over CS plus 1 over CSH, CS, CSH. So it will be CSH, CS divided by CS plus CSH. Now, the thing is, the equivalent capacitance is going to be smaller than the smallest capacitance. Okay, so then there is a frequency. So this C equivalent is going to resonate with LS at a frequency which is f1, which is going to be 1 over 2 pi root of LS C equivalent, right? So in this case, C equivalent is small, so f1 is higher. So basically this causes f1 to be higher than f0, right? So this is the resonant frequency when the switch is off. When the switch is on, so this is when switch is off. Okay, so we have a frequency f1 which is higher than resonant frequency, higher than f0, which is the switching frequency. Now when the switch is on, then CSH is shorted out. Then the capacitor CS is larger than C equivalent. So when the switch is on, okay, so then we are going to have F2 is going to be 1 over 2 pi root of LSCS. Okay, so F2 is going to be smaller than F0, correct? So now let's look at the normalized frequencies. Let's say A1 is equal to F1 by F0. Then A2 is equal to F2 by F0, right? And let's plot this as a function of Q of the network. Q of network. So why I am bringing this into question? Without Q of network, an idealized model, okay, an idealized model is also assuming a Q of a network. And if you refer to papers by Sokal, 1975, right, this says ideal Class E operation. But then when it comes to solving the equations, there is no ideal Class E operation. There is a Q of a network involved. And how it is involved? It is involved this way, that this LC combination, okay, or LSCS combination will cause a resonant frequency of F2, while the switching is as F0, right? Similarly, when it is off, the switch is off, then we have a frequency F1 and the resonant frequency is something else, right? At F0, you are going to have, so at resonant frequencies, a series resonance will cause a net resistance of or reactance of 0, right? Because we have omega L minus 1 over omega C. That would be cancelling out, right? So then you have a value of, let's say, Jx or X. Okay, so the reactive part would go to 0. So the reactive part X will go to 0 if it was so. Now that assumes that F1 is very close to F0 and F2 is very close to F0. That happens only when the Q is infinite. Okay, so when you say it's an ideal class E, okay, but then the equations which were written in that paper in 1975, okay, those equations were keeping in mind not a infinite Q but a finite Q. Otherwise the solution will not work. You will not be able to determine LS and CS if you assume a infinite Q, because in that case Jx would be 0, right? So in this case there is something called a residual Jx. So finite Q means residual Jx. Okay, so then the circuit would modify to VDD, RFC, a switch, shunt capacitor, CSH, and then this is going to be residual Jx at fundamental. So this is circuit at fundamental. Okay, and then you have got the load, which is RL. Okay, and then you have V0 and I0 over here, which are given by this equation, right? Now this is also assuming that there is a finite Q, right? Otherwise the equations will not be able to find out what is LS and what is CS, right? So in that it's an idealized class E, but then the modeling is with a finite Q. Okay, so later on we will see how to put in a Q into the equation so as to get a design at any Q. Okay, so let's say right now we have just a residual Jx. Now we will draw this. Let's visualize this. So what we have is so let's draw the voltage and current waveforms, right? So let's say the voltage is doing this. This is the load voltage. This is sinusoidal, and the current is also doing this, right? So the current is also doing this. Sorry, current is also doing this. Okay, so the voltage by current is going to be R, right? And these are given by this equation, right? Okay, so we have got C. So this is going to be VO and this is going to be IO. Now if I take focus just on the current, and let's just draw the current. So bear with my drawing, it's not so good. When we do a Matlab it will be better. So let me just draw no, I want to draw bigger. So these are current. Okay, so this is IO. Okay, so now this current IO is over here. That means if this current is IDC or ID, then the difference of the two current is going to flow here, and that's going to be a DC shifted sine wave, right? So this is a sine wave, but then I'm going to DC shift it, right? So I'm going to just DC shift it. So I'm going to select this waveform and I'll make a copy of it, and then I will do a paste of this, and I am going to shift this up to, let's say, this level. Okay, so now let me just dot this. bear with me, it will be easy to understand if I do all this. So this is the output current, which is a dotted one, right? And then you have a DC shifted sine wave which is flowing through switch and capacitor combination. So this is IDC, right? So now what's going to happen is you can just focus on the blue waveform, which is a solid blue waveform. Now I'm going to choose a point somewhere, let's say over here. So I've chosen a point over here. Okay, red color. Okay, so I am letting, so this should be red color. So I'm letting this waveform pass through the switch. So the switch is on and this passes through. And as soon as you switch off, okay, as soon as you switch off the switch, the current, instead of going through, so initially when the switch is on, the current flowing through the capacitor is 0 because this is the least resistance path, right? So all the current is going through the switch, nothing is going into the capacitor. Okay, so this red portion which you are seeing, this is all going through the switch. Then a piece of it, as soon as you switch it off, so this is going to be T off. So let's write this here, T off. So at T off, I am going to take this current and put it through the capacitor. So I have put this current through the capacitor. So I have chopped the current waveform into two points. And this, at this point, I have got T on. Correct? So I have T on here. Okay, so now the way I have done this is, okay, now you can see, so when the red current is there, the voltage across the switch is 0 because this is the 0 resistance. Okay, but the current is full. Now when you switch off, the current through the switch is 0, but the current flows through the capacitor, and the capacitor is going to integrate this. So if a capacitor integrates this, which color should I use? Can I change color? Yeah. So let's pick up this color. So a capacitor is going to integrate it. So when there is a 0 crossing, that's a maxima. So basically the voltage is going to build up like this, and at 0 crossing, which is over here, so this is the 0 crossing, right? So at this point, the voltage reaches the maxima, and after that, the voltage is going to decline to 0. Why 0? Because I have chosen these points such a way that, which color should I use? Okay, let's choose a light color. That this area under this curve is equal to this area under the curve. So when these two areas basically is integration, right? So integration of this waveform on the capacitor is the voltage. So voltage is reaching 0 at this T on. And notice that the current is also 0. So simultaneously, so at this T on, voltage across capacitor, VSH, is equal to 0. And current through the capacitor is also 0. So now when you turn on this switch, the capacitor has 0 energy stored, right? So when you switch on, then none of it is shorted to ground, right? So we haven't lost any energy in switching. Okay, so had it not been 0 energy, then we would have lost some energy to ground by shorting the switch, right? So now the three conditions which I have here, or rather two conditions which I have here. Okay, one is that when you turn on the switch, okay, voltage, the net energy on the capacitor is 0. Okay, so this is called a smooth switch turn on, right? The next thing is uh, the area under the current curve is 0, summation of area, so that's why voltage is 0, and the current is also 0, so the net energy stored on the capacitor is 0. Next thing is, when it is turning off, the current instantly dies in the switch, which doesn't happen in a transistor. So you are going to see a certain overlap when there is a T off, and that will cause the efficiency to be less than 100%. But for an ideal switch, it is going to be 100% because this drop off is going to be instantaneous, right? So this is if you have an ideal switch, then your efficiency is 100% because the overlap here, the current instantly decays in a switch when it is turned off, right? So this is also one of the requirements. Okay, so now using this, okay, now using this, what's happening is this waveform, if you see, and if you do its Fourier expansion, you will see the fundamental is there, and then the third harmonic is 17 dB down, okay, and then the fifth harmonic is way down. Second harmonic is 17. Let me see. We will see this. I'm not on the top of my head. I can't remember this. But the third harmonic is 17 dB. No, the second harmonic is 17 dB down. Sorry, second harmonic is 17 dB down. The third harmonic is way further down, right? So this waveform is basically having all the energy in the fundamental, right? And then what you do is you need this LC filter to filter the fundamental to the load, right? You are filtering fundamental to the load using this LC filter. So I can say that this this L and C combination is going to trap all the voltage harmonics, while this combination is going to trap all the current harmonics. Okay, so you have a DC in and you have got AC out without any loss, right? So that's why efficiency is 100%. Now let's go ahead and try to express this in terms of equations, right? So that that's the main topic, and then we will look at the trade-offs and stuff like that. Okay, there has been a lot of implementations and microwave frequencies also, and I'll show you 3 ways of implementing Class E. Okay, so let's quickly write down the equations, and these equations will require some little bit of trigonometry. Okay, so I am going to do basic relationships of Class E. Basic relationships of Class E, and then I will show you how to code this in Matlab so that you can write your own code, and then you can generate your Class E, and you will be able to design your Class E. Okay, so we have got V naught, and V naught is a function of theta. Okay, so then you have V naught is equal to C sine of, so let me, okay, so I'll just do it. If I do a mistake, I'll pause and correct it. Fine. So this is equation number 1. So this is the load voltage. So the load current I naught is again a function of theta. Okay, so this will be C by R sine of theta plus phi. So this is the load current. Then you have got Jx. So Vd, when you reach the drain, Vd is over here. So this Vd is equal to voltage across Jx plus the output voltage. So let me just write it down. Vd is going to be equal to C sine of theta plus phi plus Jx C by R sine of theta plus phi. So this is going to be that. Now if I absorb this j into this, then it will become cos, right? Right? So we will have c sine of theta plus phi plus x c by r sine of, sorry, cos of, because I have absorbed j into this, cos of theta plus phi. Okay, so this is going to be v d, which is a function of theta. Okay, so now I can also write this as c1 sine of theta plus phi plus or phi 1. Okay, so now I can express this as c expresses this psi, right? So phi 1 can be written as phi plus xi. Okay, so let's say I say c sine A cos B. Okay, c cos of xi is equal to c1 and c sine of xi is equal to c1 cos of, let me see, c1 c cos of xi, c is equal to c1 cos of xi. Correct. Okay, let's write this as, and c1 sine of xi, so this will be xc by r. Correct? So I am replacing c with c1 cos of xi. I am replacing xc by r with c1 sine of xi. So that would give me c1 cos of xi sine A cos B, and then c1 sine of xi cos of theta plus phi. Correct? So then Vd, so if I do that, then I can write c1 sine of theta plus phi plus xi. Right? So this would be your Vd of theta, which is same as this one, right? Okay, so now that means that if I do a square and add on both sides, we will have c1 square would be equal to c square times of 1 plus x by r square. Correct? And then that means that c1 is equal to c square root of 1 plus x over r. Right? And then you have got xi will be equal to sine by cos, right? So tan of xi, so it will be tan inverse of x by r. Correct? So this is the waveform at the drain, right? And this is the waveform at the load. Now let's start applying the constraints. Okay, so let's assume this. So I'm going to focus on the off part. So this is the off part, right? So this part is the off part. So this part which you see is the off part. So I'm going to say that this off part is going to be twice of y, and this is centered around, let's say, a phase of pi by 2, right? So pi by 2 minus y, I'm turning it off. So basically the off is between pi by 2 minus y to pi by 2 plus y. So this is the off state, right? And what is this phi? So from T off up to a point, okay, let me see here, of zero crossing of the sine wave, right? So sine wave is over here. So basically then this duration between the output waveform, so this dotted one is the output waveform, right? So I am going T off, and T off to this I am saying a zero crossing, right? Yeah, so that is phi. Okay, so that phi is over here. So output waveform is basically delayed. So the output waveform is delayed by phi from the switching waveform. So the output waveform is delayed from the switching waveform by this phi. Okay, so now for switch off between pi by 2 minus y to pi by 2 plus 5, I can write the voltage across the device. Okay, so the voltage across the device would be the integration on the capacitor CSH, correct? So Vd, which is a function of theta, would be 1 over omega c sh times of integral from pi by 2 minus y up to theta of IC u, is a function of u, or rather IC, I would say, so this is going to be through the capacitor, right? So this will be through the capacitor. So let's say ICSH, which is a function of, let's say, u and du. So this is a function of u. So I'm going from pi by 2 minus y. So I'm taking this waveform, the green waveform. Okay, that is ICSH of u du. Okay, so I'm integrating that on capacitor, and at theta I would know the value of the voltage, which is going to be this orange waveform, right? So now let's write this as, so this is going to be equal to 1 over omega CSH, and this is going to be pi by 2 minus y times theta. This is IDC minus the C over R, correct? Sine of u minus phi du. Okay. Okay. So now let's do this integral. So I will have V sh, I can write as a function of theta, would be equal to integral of that, which will be IDC times of u. So I'm doing an integral, C over R common, and this will be minus cos. So this will be plus cos of u. Should I take u plus or u minus? Let's proceed with minus. Okay, and to this I would apply the limits pi by 2 minus y and theta, isn't it? So, or rather, yeah, so in this case it will be id. Okay, why there is a theta over here? Okay, so this is going to be id times of theta minus pi by 2 plus y. Okay, plus c over r times of cos of theta minus phi. Okay, and pi by 2 minus y. Okay, pi by 2, so it will be cos of theta. Okay, I'm doing a mistake here. Let's put this as a plus sign. Okay, okay, so in this case it will be theta plus phi minus of cos of pi by 2 minus y plus phi, correct? So this will be id times of, or idc, doesn't matter, theta minus pi by 2 plus y. So this is going to be vsh as a function of theta plus c by r c by r. Okay, we are forgetting this omega csh, so it will be omega csh here. So there will be a omega csh here. Similarly, c by omega csh r, and this would be cos of theta plus phi minus 90 plus theta, okay, minus sine theta, sine of phi minus y, correct? So this is going to be my waveform across the capacitor, or rather the drain. Okay, so now let's look at its fundamental component. Okay, so the fundamental component, okay, so fundamental, it will be sine component. So let me see, fundamental of it, A1, or rather C1, right? Am I right? Because this is the fundamental, right? So this is C1, right? C1 sine of this. Okay, so C1, so I'm trying to find C1 here. Okay, so in this case C1 would be equal to 1 over t by 2. So in this case t by 2 is going to be pi, 2 pi, so I am pi, 0 to 2 pi times of the VSH, which is a function of theta, correct, times of sine of theta plus phi 1, correct, times of d theta. So this will be giving me C1. Okay, so if I'm going to integrate this, right, and then I will have this in terms of C. So I'll have C here, so I can determine C from there. So from C1 I can determine C, because the relationship is C times of square root of 1 plus x by r, right? Okay, so C here from integration would be id times of r times of, so I'm going to write the final equation here, times of twice of y sine of y. So y is half the switch off duty cycle, right? Cos of phi 1, which is going to be phi plus xi, right? plus twice of y of sine of, so you can solve this if you want, twice of y of sine y minus, oh, I'm going to run out of space. Let's do this again. Okay, so from this I'm determining C, not C1, because once I have C1 I know C. C is going to be equal to ID times of R times of something over here, which I'm going to write it twice of y. You can derive it. I have derived it number of times. Sine of y cos of phi 1 cos of phi 1 plus twice of y. Okay, this is in bracket, twice of y sine of y minus twice of cos of y, right, times of sine of phi 1. Phi 1 is phi plus xi, divided by pi omega CSH times of R and rho. Now rho is this one, so I can write this as a C rho, right, rho plus half of sine of twice of phi plus xi. Okay, so I have separated out sine of twice of y minus y sine of xi plus twice of sine of y minus phi times of cos of phi 1 plus sine y. Okay, so I can write this as ID times of R of h, and this h is a function of phi, xi, y, rho, r, omega, and CSH. Right. Now another is the quadrature of this. Now the quadrature component is 0, right? So I can write 0 is equal to 1 over pi integral 0 to 2 pi. So in this case 0 to 2 pi will be basically pi by 2 minus y to pi by 2 plus y. So that's how you have this h value, right, for that limiting case of, because in 0 to 2 pi you are only going to see off waveform, right, which is basically pi by 2 minus y to pi by 2 plus y. So now this would be v as such, which is a function of theta times of cos of theta plus phi d theta. So this is going to be 0. So this is the quadrature. So if you have a sine here, the quadrature component is 0. Where is it? Here. The quadrature component is 0, right? So I have equated the quadrature component to be 0. So in this case, I am going to get, from here also I'm going to get the same C. So C is going to be equal to I d times of R times of something which I'm going to write as a simplified form, twice of y sine of phi 1 times of sine of y, right, minus twice of y cos of phi 1 cos of y plus twice the sine of y cos of phi 1, twice the sine of y cos of phi 1, divided by minus twice of sine of phi minus y sine of y sine of phi 1. You can simplify this, minus half sine of twice of y cos of twice of phi plus xi cos of twice of phi plus xi plus y cos of xi. Okay, so this can be written as C is equal to ID times of R times of G, and G is a function of phi, xi, and y. So I have got two values of this, so I can equate this. IDR H should be equal to IDR G, correct? So from this equation I should be able to get CSH because the other inputs are given, right? So basically JX so let's see, residual JX basically implies this phi, right? And then you have given the load R, then you are given the off duty cycle as twice of Y, right? And then you are given the frequency omega, which is equal to 2 pi of f naught, switching frequency, correct? So we have omega and y, so these are my inputs. Okay, so the only unknown which will remain is CSH for a given residual, right? So that's the idea of to design, or rather to model this. Now let's look at the DC value. Okay, so G. Okay, so let's evaluate the DC value. So before that, we know that VSH, which is a function of theta, is basically going to be ID divided by omega CSH, right, times of something which is going to be theta plus pi by 2 minus y. Oh, okay, sorry, y minus, so there will be a subtraction, right? So minus pi by 2 plus y plus this is going to be C x over R, right? And C is equal to IDRG. And then ID is outside, RG. So it will be just 1 second, J C over omega CSHR. There is no X here, right? Yeah, because just 1 second. Okay, so we are looking at current, right? So from here it is C over R, IDC RG over R. So this ID is already outside, so we are left with only G. it will be G times of cos of theta plus phi plus sine of phi minus y, phi minus y. Okay. Okay. Now, to find the DC value, so DC value of V, so VDC is going to be equal to 1 over 2 pi. So this will be VDD, right? So this is the DC value. So I can write here VDD. So VDD would be the DC value of this output waveform, right? So in this case, integral 1 over 2 pi 0 to 2 pi VSH theta times of d theta. Okay, and then I can write this as 1 over 2 pi times of pi by 2 minus y, 2 pi by 2 plus y, times of theta minus pi by 2 plus y, okay, plus g times of cos of theta plus phi plus sine of phi minus y, okay, d theta. Okay, so now I will integrate this as 1 over 2 pi. This will be theta minus pi by 2 plus y square by 2 plus g cos will be sine. Integral would be sine of theta plus phi, and this would be pure number, right? Sine, this is not a function of theta, phi minus y times of theta. So this would be applied limits pi by 2 plus y, pi by 2 minus y. So when you do that, okay, so this whole thing is going to be that. So when you apply the limits, you are going to get VDD would be equal to ID over 2 pi omega c. Okay, so okay, we forgot about omega c here. So this is 1 over omega c here. Oh, CSH over omega CSH times of twice of y square minus twice of g sine of y sine of phi. I have broken that, right? Plus twice of y g times of sine of phi minus y. That's a constant. So this is the value of VDD. Okay. So then we have VDD equal to ID times of RD REC, right? And ID, so RDC would be equal to VDD divided by ID. So ID we already have, right? So where is ID? Okay, so ID is the out, right? No, ID is from here. Okay, so in this case, okay, so now from here this equation I can have RDC is equal to VDD over ID. So this will be 1 over 2 pi omega CSH times of twice of y square twice of g sine of y sine of phi plus twice of yg sine of phi minus y. Correct. So this is the DC resistance. Now let's consider a criteria of 100% efficiency. 100% efficiency. That means let's look at P out. Okay, P out is going to be equal to C square. Okay, C square by twice of R. V square by R, right? So C square by twice of R. Okay, and C is equal to IDR G. IDR G. There were twice of R. So this will be equal to ID square G square R by 2, right? And then we have PDC is equal to IDC square or ID square RDC. So this would be equal to, right? So now if I take P out divided by PDC, then ID square will cancel out. Then we have G square by 2 R by RDC. So this is going to be my another equation which is important to me. Okay, so let's put this as 3. Okay, so this is the criteria of 100% efficiency, which gives me that. Okay, now zero stored power when the transistor is on. Okay, using that I'll be able to get the other things. Okay, so that means at T on we are talking about theta is equal to pi by 2 plus y. So at that point VCSH is equal to, which is over here, VSH, right? VSH is equal to, I will put here theta equal to pi by 2 plus y. So it will be twice of y here. Okay, IDC over omega CH, ID over omega CSH, and this will be theta minus pi by 2 plus y. So pi by 2 plus y, so it will be twice of y. Okay, the next thing I am going to have is VSH, the G cos of theta plus phi, right? And theta is pi by 2 plus y. So cos will become minus sine. Okay, cos will become minus sine. So it will become minus G sine of theta plus y. Oh, sorry, there is no theta. Phi plus y. Right, and then G sine of phi minus phi, there is no term of theta there, right? So plus G sine of phi minus y. Okay, so this is at T on, and at T on I'm assuming that at T on I'm assuming that VSH will become 0. So this 0 will be equal to twice of y plus plus G sine of phi minus y minus G sine of phi plus y. Okay, so now I can say twice of y minus would be equal to So basically it will be twice of g. So if you simplify this, sine of a plus b is sine a cos b plus cos a sine b. Sine of a minus b is sine a cos b minus cos a sine b. So if you simplify this, you are going to get this as twice of g sine of y cos of y. And then you have g is equal to y divided by sine of y cos of phi. Cos of phi. Correct? So basically that means that cos of phi will be y divided by g sine of y. Then phi will be equal to cos inverse of y by g sine of y. Correct? Now okay, now let's say that the slope of this waveform is 0 because the current is 0, right? So the slope of voltage waveform is also 0, right? So dv theta by dt, d theta is the slope, right? Okay, so let's say that slope is xi. The slope is xi, so that would be 1 over vdd times of d vsh, which is a function of theta, divided by d theta, and this would be at theta equal to pi by 2 plus y. So this is a slope when the device turns on. This is a slope of voltage when the device turns on, right? So I'm not assuming it to 0. So in this case, if I do this, I am left with 1 over omega csh rdc times of 1 minus g cos of y plus phi. Okay, and then I can establish phi. So this was voltage 0, right, in the slope of voltage. So this was voltage 0. Okay, so finally I can have phi and psi in terms of slope also, right? Okay, so I can have 10 of phi is going to be equal to sine of y divided by y minus cos of y. This is half the off duty cycle, divided by yc by pi cos of y. So this is simplified form, 1 minus, this is coming from the slope, c by xi by pi times of sine of y. Okay, and then you have got 10 of xi, which is going to be quite complicated. It will be q1 sine of phi plus q2 cos of phi plus q3 cos of twice of phi plus gy divided by q3 times of sine of phi, okay, plus q2 sine of phi, q2 sine of phi plus q3 cos sine of twice of phi minus q1 cos of phi. Okay, so this is that, where q1 is equal to minus twice of g sine of phi minus y, okay, into sine of y minus twice of y sine y. Let me see if I'm recording. Yeah, okay, and q2 would be equal to twice of y cos of y minus twice of sine of y, right, and q3 will be equal to g by 2 times of sine of twice of y, and then x over r is equal to 10 of xi, right, then x is equal to r 10 of xi. So here I have that, then CSH is equal to, I can find out CSH as sine of twice of y sine of twice of phi divided by twice of pi y omega r y minus 10 of y. Okay, so now we have all the equations. Okay, we have modeled the Class E amplifier for any slope at turn on. So let's write a Matlab program, okay, to evaluate that. So I am going to write a Matlab program following this, right? So we have the design equations here, or the modeling equations, right? And the modeling equations I can just sum it up here. Okay, so we have got twice of y as the duty cycle, off duty cycle. Okay, and then we have got tan of phi is equal to that number, right? Tan of phi is over here. This is tan of phi. So we have got slope as xi. Okay, so let me just write down slope as xi. So this is the slope of voltage at turn on, voltage at turn on, correct? And then you have got tan of phi would be equal to this thing which we have derived here, right? No. Copy, paste. So this one comes over here as this. So this is my tan of phi. So from this, okay, I am going to get phi. Okay, so once I have phi and y is already there, okay, so I would have CSH. So once I have this phi figured out, phi is figured out now, so from phi I would have CSH, shunt capacitor, right? CSH would be this number. So this is a function of phi and y, r and phi, y and r, right? Copy, paste. So this is your CSH. So once you have figured out phi, you have figured out the shunt capacitor. Okay, so once you have the shunt capacitor, you or phi, you can find out these, because you have phi and y and g, right? So g would come from here. So you'll find out first g, isn't it? Yeah, so you'll find out g, and the g is over here. So this is g, right? So I am going to copy that. So this is your g. Copy, paste. So this is your g. So once you have your g figured out, so then you are going to do is you are going to figure out xi. So for that you are going to use q1, q2, q3 and phi. So you will be able to figure out xi. Okay, so I will copy this one. What happened? Okay. Somehow I'm not able to select this. Oh, crazy. Okay, doesn't matter. I want to copy this guy. Lasso tool is now working. Copy, copy, paste. Can I do another paste here? Okay. So I have got xi. Then I have got x, r times of 10 of xi, right? Xi. Okay, so now I have CHH and residual JX. So I have designed a class E or modeled a class E. Okay, so then I'll be able to plot the waveforms. So very quickly I'm going to write the Matlab program and I'm going to put you on a pause. Okay, so now I have used these equations. I have written them to design a class E. Okay, so let me just explain you what this is. Okay, quickly. So we have off duty cycle as D. So this is specified as a percentage D here. So then y would be, twice of y will be d by 100 into pi, 2 pi. D by 100 into 2 pi will be twice of y. So y is going to be equal to d by 100 into pi. So that is your duty cycle. Then my frequency input is going to be, let's say, whatever design or switching frequency. So the omega is 2 pi f. Then 10 of phi is this. So this is your 10 of phi. So this is your 10 of phi. So I have written 10 of phi over here. Then phi would be A10 or 10 inverse of 10 of phi. So that way I will get phi. So once I get phi, I will find out g. So from phi, I will find out g. G is y by sine of y cos of phi. So here I'm finding out g. Once I have g, I would have, for a given r, I would have rdc. Okay, so basically if you have g, you have got r square by 2 r by rdc equal to 1. So rdc equal to g square by 2 into r. So I have got rdc. Then idc is equal to vdc by rdc. So this will be the dc current. So once you have dc current r and g, you can find out the amplitude c. Okay, and then once you have that, you have got phi, you can also find out the shunt capacitor csh. Then you can find out xi. Okay, so that xi is basically over here. This 10 xi is equal to q1 times of that, right? So then 10 xi is equal to q1 times of sine of phi. Okay, so that's that equation. And once you have 10 of xi, so xi is equal to tan inverse of 10 of xi, then you have got x is equal to r times of 10 of xi. So x is equal to r times of 10 of xi, so you have x. So this way you can design a class E ideal with a residual jx. Okay, so now I will write a equation for write the function for plotting these waveforms, right? Okay, so let me put you on a pause. Okay, so I have written another script file which uses the design over here. So this is the design, and I can specify what frequency I want to design for. So let's say I'm designing for 10 gigahertz with a duty cycle of 50%, and I'm giving a slope of 1 right now. Okay, so slope is 1, duty cycle is 50%, and frequency is 2 gigahertz, right? And the resistance is 1 ohm, right? So my load is 1 ohm. So now I am going to just run it and see if I get my class E waveforms. So this is the design over here. So this ideal class E is the design, and then what I'm doing is I'm just plotting these waveforms, okay, over 2 pi, or rather 4 pi, right? So I'm plotting these waveforms over the time period of 4 pi, or rather in terms of nanoseconds, right? Have I specified that? No. So I'm going to specify time here. So time I have computed in nanoseconds, so it's over here, right? So don't worry about that. So let's run this. Okay, so to run this script, hang on, command window is over here. So this is my command window. What happened to my command window? Okay, okay, so I'm going to run this. Okay, class E wave. Okay, so here I have, let me just edit this so if you are not able to see the waveforms, let me just edit it. Let me put this as a brown color. So it's not 30%, it's 50%. So come on, so slow. Okay, I'll run this again. Okay, I'll just change it in the program. Okay, so I'm plotting this for 50% duty cycle. So let's put here 50%. Okay, and my voltage waveform switch is magenta. I want to put here red color, and I load is also red color, right? So it's okay, doesn't matter. I can put here a dash. Okay, so I can put here a dash. Okay, fine. So let's save that and let's run that. Oh, it didn't change to magenta to red. Just 1 second, bear with me. What did I do here? plot. So ICSH, so this is not ICSH, this is V switch sine, so this will be red dotted. That's okay. And then I'm gonna just run this. Okay, so now you can see that I have for a 50% duty cycle at 2 gigahertz I am plotting 2 such cycles, and I am having a voltage waveform here, and then I'm having output waveform, which is the magenta is through the capacitor, the green is through the green one is through the switch current, and then the voltage across the current, the switch is the red one, and this is a class E, right? Now I can do few more things with this code. I can specify the slope to be something else, right? So I can plot slope as let's say -3. So let's go to slope of -3, right, and or rather -3, right? Okay, and this time I don't want to close all. I want to plot it over the figure itself, right? So close all is not there, right? And figure 1 is there. Yes, figure 1 hold on, right? And grid on and hold off. So right now I have a figure 1 with the slope of 0 here. Okay, let's run this again. Save. Oh, it has put the let me just control. Okay, save it. Our duty cycle slope. Okay, so there is a mistake here. Let's put here 1. This is VDD, and the slope is over here, and the slope value is 0 here. Okay, so let's plot this again. Okay, save it and run it. Okay, so this is with the 50% duty cycle, slope of 0. Now I go back to the program and put slope as -3, -3, and in this case okay, I'm going to remove close all, and then I'm going to run this again. Okay, so now this is a plus slope. Okay, so the slope is +3. Okay, now let's see slope of -3. So this is slope of -3, so let's see slope of +3, positive slope. Okay, save it and run it again. Okay, so now you can see here. So I have designed a class E where you have a slope of this voltage waveform to go to 0, and that is your psi value, and then slope of -3 and slope of +3, and all of these are class E. Now I can also change the duty cycle, right? So right now the switch off duty cycle is 50%. So if I increase the duty cycle, off duty cycle, right, So then what you're going to get, okay, you're going to get the smaller time to integrate over capacitor, so the voltage is going to be lower. So let's go ahead and do that. So let's put back the slope to 0 and then put your duty cycle to, let's say, 70%, and let's hit run again. So let's just save it and hit run again. Okay, so now I have reduced the duty cycle. Graphics is troubling me. Okay, so now you can't make a lot of stuff here, so let's do another set of graphs. Okay, let's go back to this and say I have a duty cycle of 50%. So let's plot that first. Save it. Okay, so that's 50%. Let's look at a duty cycle of 70%. So let's go back and put here a duty cycle of 70% and just simulate this. So that's the duty cycle of 70%. So the voltage is lower, right? You can see here slope is 0 in both cases. So one is 70% duty cycle, other is 50% duty cycle. So the voltage across the device has gone down. Now let's look at the slope of 30%, switch off slope. Now it is going to integrate for less time, right? Switch off. So now save it and run it again. Okay, so that's your 30%. Okay, so that's being said. Okay, so I am able to design and plot the waveforms. What about the shunt capacitor? So for a designer, what is important? For a designer, what is important is this. So let's go back to where I was writing. Okay, so for a designer, what is important is CSH. Okay, so if you want to implement at a certain frequency for a certain duty cycle, right, and for a certain slope, right, so if the CSH is smaller than the device output capacitance, so the ideal circuit is over here. Okay, so the ideal circuit is over here. Now this CSH has two parts. One is going to be CDB of the device, and then you are going to have CSH dash. So this is the external capacitance which you are going to add. CDB is the output capacitance of the device. So if the output capacitance of the device is larger than the computed CSH, then you will not be able to design this Class E. Okay, so in that case, you only few options you have. Okay, the options you have is to change the duty cycle, right? Because frequency is your desired frequency for which you're going to design. Then only options you have is change the duty cycle or change the slope, so as to get the value of CSH, right? And the CSH in worst case would be same as the CDB, output capacitance of the device. So if the output capacitance is large for a given frequency, you may not be able to design because it exceeds CSH, right? In that case, what you do is you design for a different duty cycle. Then you will be able to design a Class E amplifier. So in next session, I will show you this constraint of JX, right? So JX doesn't let me get the values of the series L and C. So once I relax that JX, okay, so JX is a number which doesn't give me a unique solution for LS or CS, right? So once you specify a Q, then you will be able to find of LS and CS. But still here you will be able to design it. Why you will be able to design it? So let's say let's say okay, let's say over here, right? So still you will be able to design it. What you have to do is you take the current voltage waveform and current waveform, and you do divide the voltage waveform by current waveform. So what you're going to get, okay, so what you're going to get is, so let's say you are designing, you know the output capacitance of the device, right? So all you have to do is looking into the load network, what should be your Z fundamental. So Z fundamental will be equal to V fundamental divided by I fundamental. So you have V waveform, I waveform. So once you do a V and V divided by I, you know what is the fundamental impedance. Then you take the second and the third harmonics, right? So second harmonic, and you will find the second harmonic impedance. Okay, so like this. So if you have a waveform and you have a Fourier expansion of that waveform, you can take the coefficients and take their ratios. You'll get the fundamental impedance, you'll get the second harmonic impedance, you can even get the third harmonic impedance, right? So to design a class E, all you have to do is you create an open circuit at fundamental, second harmonic, third harmonic, and then you put in here a stub, right? So you can generate a matching network here where you can generate a certain fundamental, second harmonic and third harmonic, and then you will be able to get the same class E response. So even if you have a J-ax, okay, which is basically depending on the Q of the network, and we haven't discussed the Q of the network, you can still design a class E if you know the fundamental impedance, the second harmonic impedance and the third harmonic impedance, and all other harmonics are insufficient, right? So you'll be able to design a class E just with this program. But then it is good to incorporate Q into the equations to be able to design class E. So in the next session I'm going to design a class E for any Q, right? And that will be the complete design, right? Okay, so I'm going to finish here, but before I finish I am going to show you something. Okay, so I have written that down, the program, and that program I'm going to just run it for you. And later on I'll show you how I wrote this program. Just one second. Okay, so I have written this program for incorporating any Q. Okay, so here I'm able to mention the same thing, resistance of 1, a duty cycle of 50%, and slope I'm assuming 0, and Q I'm assuming to be like 8. Okay, and frequency I'm designing for is 2 gigahertz as earlier, right? And then I'm gonna say calculate too small a value of load resistance. Okay, clear all. Okay, so let's say load resistance is 1, switch on duty cycle is 50. So there are certain restrictions on this, so let's see, Q of 4, and I'm going to design it 2 gigahertz. That's strange. Too small Q for for this duty cycle, increase either okay, or rather increase the resistance, because this is 1 ohm, right? So I'm going to clear all. I'm going to design it for 50 ohm, for example, doesn't matter. 50 ohm, duty cycle of 50%. Okay, and load Q network is 8 and frequency is 2 gigahertz. Okay, calculate. Okay, so I have got this voltage waveform which is red. This current through the switch is blue, right? And the remaining is going to flow through here, and the values which I have computed here is 0.31 picofarad, 9 picofarad, 0.234 picofarad, and this LS and CS I could get because I have specified the Q. So if I change the Q, that value is going to change. So let's put a Q of 18, and I'm going to calculate again. Okay, so now you see the shunt capacitance hasn't changed much, but this, if you see LS and CS, they have changed, right? And let's say if I design for a Q of 4, okay, and say calculate. So you see the shunt capacitance hasn't changed much, but you see the LS and CS. So basically this is deciding the residual JX, right? So Q basically is computed. If Q is known, then JX can be split into LS and CS, right? So that's the whole idea. Okay, so I'm going to stop the session here. Thanks a lot. Thank you.